one-on-one. Okay, so with that, we're going to start hopefully 1 minute early with our first speaker. So if you want to go ahead and share. Does he have the right? Okay,
Yeah.
looks like it's working. Awesome. Thank you, Bjorn. Take it away. I will jump in and let you know when you have 1 minute remaining.
Okay, thank you very much. So I talk about CP conservation in the strong interactions, and my collaborators are Bjorn I, Juan Cruz, and Carlos Tamarit. So here's this outline of the brief talk. I argue that the strong interactions conserve CP, and to do so, I go through the standard approaches, namely functional quantization and canonical quantization. And because my conclusion will deviate from the standard one, I will also point out, of course, where the issues are in the standard approaches and how they are to be fixed. And then eventually I discuss how the conclusions about strong CP show up in the effective Lagrangians that we use in order to describe the strong interactions at low energies. Okay, functional quantization. So the centerpiece of the discussion is this topological term, and the topological term is parity odd. That's why we are discussing it, and it is a total divergence. Now, since it is a total divergence, there are no perturbation theory vertices because these would be proportional to the sum of all momenta and are therefore zero. And therefore it behaves unlike from other Lagrangian terms. But the fact that it is a total divergence also opens up the possibility to study non-perturbative effects through topological properties and surface integrals. And this can play out in the following way. So omega is a four-dimensional space-time volume, and that is assumed that the gauge potentials go to a pure gauge on the surface of this volume, and that moreover this surface is topologically equivalent to a three-dimensional sphere. Then this volume integral over the topological term, or equivalently the surface integral over the associated current, evaluates to an integer number. And this is a reflection of the fact that the maps from the three-dimensional sphere into the SU2 subgroups of the SU3 of strong interactions decompose into topologically inequivalent classes that can be labeled by integers. Now the question is, how do we realize these peculiar conditions? And the first thing that is important here is that we should take time to infinity. That is because observables that we compute from pure gauge boundary conditions on finite surfaces do not correspond to ground state expectation values. Instead, for finite time amplitudes, we would have to project on a vacuum wave functional that I construct here from the projection of the vacuum on a position eigenstate. And here is then a path integral between two field configurations, and this path integral then needs to be weighted by this extra integral and these wave functions so that it maps on the vacuum wave functional. So this is easier said than done because the principal problem here is that we don't know the ground state wave functional in an interacting theory. And the common way out is to analytically continue time and then make use of the fact that the time evolution operator for this continued time in the limit of taking the time interval to infinity becomes also a projection operator onto the ground state. And this is how Euclidean theory in the limit t goes to infinity tells us the vacuum correlations without bothering about the ground state wave functional. Okay, so how do we get then integer delta n from this? So we take time to infinity now, and we ask what are the relevant contribution to the path integral. And these are those of finite action. And this means that the gauge fields, the physical gauge fields have to go to zero at infinity. And this means that the gauge potential has to go to pure gauge. Now that we take time to infinity, we can also take for our space-time R4, and we can identify the boundary as being topologically equivalent to a three-dimensional sphere. And this is how we can arrive at the fact that we are dealing with integer topological sectors. Now in this chain of arguments, integer topological sectors arise as a consequence of taking the space-time volume to infinity. And this is important for the path integration because this imposes a certain order of limits when evaluating the path integral, namely that we can only assume and sum integer topological sectors after taking the space-time volume to infinity. Now this is not a choice, and it is also our only difference with the conventional approach, because in the conventional approach, one exchanges this order of limits, and this is not justified and also leads to different results. More technically, we could also come to the same conclusion starting from, again, infinite spacetime volumes by systematically constructing and parametrizing the path integration contours from steepest descent flows. And then we see that the continuously connected parts of these integration contours are those of integer delta n. And on each of these contours, there's no upper limit on the spacetime volume. And again, this imposes this order of limits. Now, what is the consequence of this order of limits? And the simplest example that gives rise to illustrative results may be a single fermion in the dilute instanton gas approximation. Here I give a mass to the fermion so that we can't remove the CP violating phases by chiral field redefinitions. Then next thing is we calculate the fermion correlation function in a fixed topological sector and now include the strong interactions. And the strong interactions will contribute extra chiral symmetry breaking via the chiral anomaly in addition to the one from the mass term. And this extra contribution can be calculated from the Green's functions of the massive fermion in the background of an instantron. And these Green's functions in a fixed topological sector don't know anything about theta because in a fixed topological sector, the topological term just integrates up to a constant. And therefore, these extra contributions in fixed topological sectors align with this phase here alpha. And then when we sum over this topological sector, this alignment remains intact. So here are the new contributions induced by the chiral symmetry breaking, and the phases here are aligned. If we are, however, choosing to exchange the order of limits, the following is happening, that this phase here, the new phase from the chiral anomaly, realigns with theta. And this is because the topological sectors with small delta n get suppressed by destructive interference, and we are only left with the outliers that have a large delta n. Now, in the latter case, we have here two relative phases, and in general, we can't remove them by a field redefinition, whereas in the former case, so that there's CP violation, whereas in the former case, these phases align and we can remove them both together by a field redefinition, so CP is manifestly conserved. Now, this conclusion carries over to more general expectation values, and it is not relying on the dilute instanton gas approximation, but it really only relies on sticking with the primary order of limits. So inasmuch as the strong interactions inasmuch as Euclidean path integrals in the infinite time limit give us the vacuum correlators, we can conclude that the strong interactions conserve CP. So next thing to ask, of course, is whether we can confirm this from the point of view of canonical quantization. This is not only a consistency check, but it has also maybe some practical implications because it opens the possibility to understand finite VT problems. For example, importantly, periodic temporal boundary conditions that are often used in lattice calculations and that correspond to the trace of the canonical density matrix. And to make sense of this trace, we need to know what the properly normalizable physical states are that we want to trace over here. So let's do it. Let's choose temporal gauge and calculate the canonical momentum conjugate to the vector potential. This is given by the electric field, plus a term that is proportional to theta and to the magnetic field. The good thing about temporal gauge is that it gives rise to very simple and manageable operator commutation relations. In particular, these can be implemented by representing the canonical momentum by the derivative with respect to the vector potential. Now, the Hamiltonian density then is just the energy density of the gauge fields, and in operator form, it looks like this here. Now, in temporal gauge, of course, there's a large residual gauge freedom, and this consists of all space-dependent gauge transformations. So next thing we need to do is must talk about this extra gauge freedom. And an important tool, a useful tool to analyze these gauge transformations is the Chern-Simons functional, which is the flux of this topological current through a spatial hypersurface, which is now just the integral over space. What then is commonly done is that one imposes an extra constraint, that is that U should go to a constant on the surface of the volume. Now, this is exactly the point where I'm going to deviate here. I'm not going to follow and I'm not going to use this extra constraint, but let's just go with it for the moment and see what this implies. Then we can identify all the points on the boundary of the volume and we can compactify it and we again get a three-dimensional sphere. And a consequence of this is we again have homotopy, and here this leads to equivalence classes of so-called large gauge transformations. And these large gauge transformations have the property that they are not continuously connected with the identity and that they change the Chern-Simons functional by an integer number of units. Another important thing to note at this point is that the canonical formalism tells us that the wave functional transforms under gauge transformation in the normal subgroup, that is particularly the subgroup that is continuously connected with the identity, trivially, so it is gauge invariant, and this is equivalent to the Gauss law, and this is how the canonical formalism observes the Gauss law. Now, is there any good reason for restricting these gauge transformations at infinity? And here's a snippet that may suggest that since back on the days, such a good reason may not have been there. Nonetheless, it has become something that has been commonly, oftenly, and also often tacitly assumed. My take on this, however, is that this extra constraint is not enforced in temporal gauge only. To enforce it, one would have to make extra provisions, for example, add Lagrange multipliers. And this would then lead to modified commutation relations, probably something very messy. I'm not aware that anybody attempted to do this. So the only difference here with the standard approach is that I will carry out canonical quantization without the extra constraint. And before I explain that, let's look at what is happening with the extra constraint. Now we have these large gauge transformations, and these give rise to non-trivial one-dimensional representations under which the wave functional can transform. Now, even though SU3 is a simple abelian group, these one-dimensional representation can exist because these large gauge transformations are not continuously connected with the identity. Often in the literature, one constructs states that have this transformation property from superpositions of field eigenstates that are pure gauges, and these are then the so-called theta states. Now, apart from the fact that there seems to be no reason for this extra constraint, and this has not been technically implemented in the canonical quantization, I see the following issues here. The states here, whether those or the theta states, they are not normalizable in the proper sense. They're normalized to a Dirac delta function. And this raises the question whether these can be physical states, because physical states, according to the axions of quantum mechanics, must be properly normalizable. Of course, there is an analogy here with Bloch waves. And hello?
What is here?
Hello?
Sorry, Bjorn, someone joined in unmuted.
Okay, I'm sorry. So obviously here there's an analogy with Bloch states, and so mind that Bloch states are also not properly normalizable, and therefore they are not the physical states that, and they're also not members of the Hilbert space. The states that are physical and that are within the Hilbert space are wave packets that are formed from the Bloch states. And these wave packets on the crystal, they are not translational invariants. And translational invariance in this analogy corresponds to gauge invariance on the side of these theta states. And of course, we don't want to break gauge invariance, so this is not an option. Now, when one thinks about this for the moment, one sees that when calculating inner products from these states, the summation over n implies that in this inner product, we sum over infinitely many gauge redundant configurations. And this is at odds with the usual approaches to gauge fixing, where we aim to count each physically inequivalent configuration one time and one time only. One could attempt to naively restrict the inner product to a single gauge copy, but this would also not be acceptable because then the theta vector would no longer be orthogonal. So let's see how this works out without the extra constraint. In the Hamiltonian, we have a cross term here, a non-diagonal term. And this term does not admit separation solutions so that we could bring the wave functional to a form where the gauge transformation property becomes clearly visible in a separate factor. Now, what we're going to do, therefore, is we diagonalize the Hamiltonian, and this can be done when we realize that the functional derivative of the Chern-Simons functional with respect to the vector potential just gives us a magnetic field. And thus, we see that with this unitary transformation, we can just simply remove this term, and we end up with a Hamiltonian that is diagonal, and therefore allows a separation ansatz when solving the Schrödinger equation. Now, the Hamiltonian is gauge invariant, and therefore the solutions or the eigenstates of the Hamiltonian can be organized in representations of the gauge group. And to have gauge independent probabilities, the gauge transformations should be pure phases. And since now we can separate the gauge dependence, this phase can be isolated in a single factor. This means that, okay, And now, since there are no extra constraints on the gauge transformations, namely all of these transformations, so we drop the constraint that u should go to a constant infinity, so all of these transformations are now continuously connected with the identity. There are only trivial representations, so this phi has to be chosen identically 0, and therefore psi is gauge invariant. And gauge invariance here means that there's no theta dependence in the prime basis. So in the prime basis, all expectation values are CP conserving because there's no theta dependence in the Hamiltonian either. And since this is a basis independent statement, it carries over to all bases, and therefore CP is conserved. Now that we have fixed the gauge transformation property of the wave function, we can also fix the residual gauge freedom, and therefore the physical states are properly normalizable. And with these properly normalizable states, we can now also make sense of the trace of the canonical density matrix. And when promoting this, when deriving path integral, then it turns out that this samples over all topological sectors, but without theta-dependent phases. Okay, let's finally talk about effective Lagrangians, and let's make a spurion analysis. The symmetry of interest here, which is explicitly broken, is U1A, and it is explicitly broken by the chiral anomaly and by the quark mass matrix. This means that in the fundamental theory, there are two associated spurions, namely theta and the phase of the quark mass matrix. Then we can follow Toft to integrate out the topological effects in the dilute instanton gas approximation, and we obtain this effective Toft vertex. And from the point of view of spurions, we should promote this phase here, psi, to spurion field in such a way that this new effective Lagrangian becomes invariant under these U1A transformations. And we see that we could choose psi equals theta, and it would be invariant, but we could just as well also choose psi equals minus alpha bar, and it would also be invariant. Now, in the dilute instanton gas approximation, we can actually calculate what this is. And so we sum over the topologies, and in the primary order of limits, we find that psi equals minus alpha bar. And in the exchanged order of limits, we find that psi equals theta. And both outcomes are consistent with the spurion analysis. And therefore, the spurion analysis does not tell us whether the effective theory has to conserve or violate CP, but we really have to go to the underlying level to understand this. And this is also what is happening in the chiral perturbation theory description of the strong interactions. So this is based on a nonlinear sigma model, and we write down an effective Lagrangian. And this effective Lagrangian becomes invariant under the axial U1 and under the additional flavor symmetries, provided we promote the quark mass here and this parameter xi to the spurion fields. And again, for xi, we have we see that the Lagrangian is invariant under U1A if xi equals theta, or is also invariant if we choose xi equals minus alpha bar. In the case xi equals theta, the chiral condensate here, when we minimize the potential alliance with theta, and CP is violated because there's a relative phase with the quark mass matrix. In the case xi equals minus alpha bar, the chiral condensate aligns with the quark mass matrix and CP is conserved. So again, considering the EFT alone, therefore does not lead to a conclusion regarding strong CP, simply because we have two spurions to play with. The eta prime meson, which gets a mass from this explicit breaking of U1. Here I choose a determinant. It could be also any other term that breaks U1A. And therefore, none of these options, or both of these options, are consistent with having a massive eta prime meson and explicitly broken U1. So nonetheless, this has been the fact that we can get a massive eta prime from the primary order of limits has been recently questioned by arguments based on topological susceptibility. So let's talk about these ones briefly. So the topological susceptibility is the infrared limit of this correlator of the topological term. And the large N analysis then leads to the important result that we can compute the eta prime mass in terms of the topological susceptibility from the quarkless world. And it turns out that both are proportional. Now, it has recently been claimed that for a model of a quantum mechanical rotor, the quantity that is analogous to the topological susceptibility would be 0 when using the primary order of limits.
1 minute remaining, Bjorn.
And this would imply a vanishing mass for the eta prime meson if this would transfer to QCD. Now, in this analogy, we should identify FF tilde with the angular velocity. And in the simple model, we can simply calculate what is the correlator that corresponds to the one here. And it turns out to be of the following form. We have imposed here certain boundary conditions that stipulate a given topological sector. And to project on the vacuum, of course, we need to take again t to infinity first. And then the boundary conditions become irrelevant. And when we then carry out this remaining time integral that corresponds to this integral here, we conclude that the rotor has a non-vanishing susceptibility. So if this has any bearing for QCD, we would see that there's no conflict with U1A breaking and having a massive eta prime meson. So here's my summary in functional quantization. We have argued that the primary order of limits has to be observed, and this is because integer topological sectors only follow from infinite time or infinite space-time. In canonical quantization, we have argued that A not equals 0 does not imply U going to a constant at infinity. As a consequence, all gauge transformations are continuously connected with the identity, and therefore they are sitting in trivial representations of the gauge group. And in either case, we conclude that CP is conserved. Effective field theories alone do not decide the question of CP, and therefore it is really necessary to go at the underlying levels. And I have shown which points are exactly the ones that are relevant for the conclusions regarding strong CP. And I look forward now to discussing these points with you, and I would like to thank you for hearing me out.